When we solve a system of linear equations, the usual way to do that is to manipulate those equations until they reach some kind of simple form from which you can read off the solutions, if there are any. We can represent systems of linear equations in their matrix form, and we know that manipulating the equations corresponds to doing row operations to the augmented matrix. So what we'd like is a simple form which we can get to by doing row operations from which we could read off the solutions to the matrix equation. And that simple form is going to be called row-reduced echelon form. We're going to define it later in this video. But before we do that, we need to know that this procedure actually works. In other words, that when we do row operations to get to our simple form from which we can find the solutions of the system we end up with are the same as the solutions of the system we started with. Otherwise, this idea wouldn't work at all. So what we need to prove is that if you've got an augmented matrix like this one, and you do a bunch of row operations to it and end up with a new augmented matrix, this one, then the solutions to the old matrix equation, ax equals b, are exactly the same as the solutions to the new matrix equation, a prime x equals b prime, that you got by doing row ops. So how can we prove this? First observation is that it's enough to do the case when the new augmented matrix arises from doing a single row operation. Because if we know that if one row operation doesn't change the solutions, then doing another row operation also won't change them, and another won't change them, and so on. So it's enough to do the case when A prime is the result of doing a single row operation R to A, and B prime is of course obtained by doing the same row operation to B for some row op R. Okay, what do we have to show then? We have to show that if something is a solution of the new matrix equation, then it's a solution of the old matrix equation, and if something's a solution of the old matrix equation, then it's a solution of the new matrix equation. So let's suppose that we've got a solution of the old matrix equation. So we'll call that U. So A times U is equal to B. And we have to show that U is also a solution of the new matrix equation, A prime x equals B prime. Okay, well, just do the row operation to both sides. So R of AU is equal to R of B. Okay, now we know that doing a row operation is equivalent to left multiplication by the corresponding elementary matrix. And the corresponding elementary matrix is what you get by doing R to the appropriately sized identity matrix. So what we've got here is row R of I, the elementary matrix corresponding to R, times A times U is equal to, well, R of B is B prime. Okay, but we can bracket this here. Let's bracket this like this, because now we can notice that R of I times A is the same as R of A. Which was our new coefficient matrix A prime. So what we've got is that R of I times A, that's A prime, times U is equal to B prime. Right, we have shown that if U is a solution of the old matrix equation, then it's a solution of the new matrix equation. Now we have to show the other way round. So let's suppose that A times, we'll call our solution another, A prime times our new solution V is equal to B prime, and then we have to show that V is also a solution of AX equals B. But you can do this just by doing the exact same argument, only with the inverse row operation r to the minus 1. So we're done. Row ops don't change the solutions to the matrix equation that you do them to. So now we're almost ready to define this simple row-reduced echelon form to which we're going to be able to reduce augmented matrices by doing row ops, and from which we're going to figure out the solutions to a matrix equation. And to do that, to define row-reduced echelon form, I need the notion of a leading entry. The leading entry in a row of a matrix is the first non-zero entry in that row starting from the left. So if we look at this example here, then the leading entry in row 1 is this thing here. So this is the row 1 leading entry. In row 2, the leading entry would be this one. But if you look at row 3, there are no non-zero entries. So row 3 does not have a leading entry. Okay, so we know what the leading entry in a particular row of a matrix is now, and we know that it may not have a leading entry if the row is all zeros. So now we can define the row-reduced echelon form of a matrix. We can define row-reduced echelon form. So a matrix is said to be in row-reduced echelon form, which I will always abbreviate to RREF, if it's got the following 4 properties. Property number 1 is that if a row contains a leading entry, then that leading entry has got to be 1. Property 2 says that if you've got any all zero rows, so rows with no leading entry, those have got to be at the bottom of the matrix, so below any rows which are not all zero. Property 3 is that if you've got a leading entry in a particular column, every other entry in that column must be 0. And property 4 says that if row I and row I plus 1 both have a leading entry, then the leading entry in row I plus 1 is strictly to the right of the leading entry in row I. So this is quite a complicated definition. Let's look at some examples of matrices which are or are not in row-reduced echelon form. So I'm going to begin with this one here, and you should pause the video and figure out for yourself, is that in row-reduced echelon form or is it not in row-reduced echelon form? The answer, of course, is no. And the reason is that it's got a row of zeros which is not at the bottom. So it breaks rule 2. So there is a row of zeros which is not at the bottom of the matrix. It's got another row of zeros. It's got a non-zero row below it. Okay, move on to the next one here. Again, is it in row-reduced echelon form? You should pause the video and think for yourself what the answer is. Again, the answer is no. It's not in row-reduced echelon form. And the reason it's not in row-reduced echelon form is, well, it obeys rule 1 because the leading entries are 1. So there's a leading entry in row 1 and row 2, and they're both 1. It obeys rule 2 because there aren't any 0 rows. It obeys rule 3 because if you look at the column of the leading entry in row 1, that's this column here, and all the other entries except for the leading one are 0. And equally, if you look at the column of the leading entry in row 2, so that is this column here, again, all the entries except for the leading entry in row 2 are 0. So it's fine with rule 3 as well. But it doesn't obey rule 4 because the leading entry in row 2 is not to the right of the leading entry in row 1. So rule 4 is violated in this case. Okay, moving on, let's do this one just here. So this one, again, pause the video and think. Again, this one this time is not in row reduced echelon form, and this time there's a leading entry which is not 1. So the leading entry in row 1 is 2, and that leading entry is not equal to 1. So this is not in row reduced echelon form. Okay, next let's do this thing right here. This thing, well, this time I've got some numbers a and b, so variables a and b, and I'm going to think about what happens according to the values of a and b. So if we think about the leading entries here, we think about rule 1. Well, there's a leading entry in row 1, and it's this thing, and the leading entry is equal to 1, so we're okay. And in row 2, there's a leading entry, and it's this thing, and that leading entry is equal to 1. So we're fine with row 1. With rule 1, sorry. We're also fine with rule 2 because there are no 0 rows. Rule 3 is where it gets interesting. So if you look at the entries in the same column as the row 1 leading entry, that's this column here, then you're fine. But if you look at the entries in the same column as the row 2 leading entry, that's here. So if we're going to obey rule 3, then A must be 0. On the other hand, rule 4 is absolutely fine because rows 1 and 2 do have leading entries, but it's true that the row 2 leading entry is to the right of the row 1 leading entry. So the row 2 leading entry is there, and it's to the right of the row 1 leading entry here. So this is in row reduced echelon form if and only if A is equal to 0. If and only if A is equal to 0. Okay, final example then, let's look at this one here, and this thing is in row reduced echelon form. It truly is a row reduced echelon form matrix. So if we think about the conditions one by one, the leading entries are here, and they're both equal to 1. Next, any 0 rows are at the bottom. Well, there is a 0 row, and it is at the bottom of the matrix. And condition 3 asks about the entries in the same column as a leading entry, and you can see if we look at, let's do them one at a time, the row 1 leading entry, all of the other entries in that column are 0, and the row 2 leading entry, all of the other entries in that column are 0, and there is no leading entry in row 3, so rule 3 is fine. And finally, there is a leading entry in row 1 and a leading entry in row 2, and the leading entry in the row 2 is to the right of the row 1 leading entry. So this is in row reduced echelon form. And just to make this absolutely clear, if I added another row of zeros at the bottom, then it would still be in row reduced echelon form. You are perfectly allowed to have more than one 0 row, so long as any 0 rows, no matter how many they are, have got to be below any non-zero rows.